So these are the notes for chapter 4 on moments and couples. So the definition of a moment is the tendency of a force to rotate a body about a point or axis. So far we've only been talking about forces sort of pressing on things linearly, but this is actually that tendency for a rotation. So think torque. A lot of the tools and stuff that you use produce that turning effect. So in other words, a force is creating a turning effect. An example of this, and I like this example, it was out of a book that I read, but they give this example of a student in a physics class not really understanding the real world, but being really good at textbook solving. So he had just taken a physics class on things, on forces and moments and that sort of thing, and he got the highest grade in this class of like 150 students. And it was in a really old lecture hall with really big, heavy doors. And after the test, he went to walk out of the classroom, and he'd pushed the door from the center, so he couldn't get enough torque to actually open the big, heavy door. And another guy walks up that had done pretty poorly on the exam, but he said, this is the reason that we have doorknobs, is because it creates a larger moment arm, so then we can actually push with less force. So if you think about that, a heavy door, or any type of door, we always have the doorknobs on the side of the door, not at the center. If we had it at the center, we'd have to have more force to actually create that same turning effect that we would out of this side. So that's just a sort of a real world example for you. The two important components of a moment are the moment arm, which I just mentioned, and the force. And for these moments, you also have to have magnitude, distance, point, and units. So there's a lot for us to know about these. When we're dealing with 2D moments, so 2D moments, sometimes we can do things that are, or we can do them in a scalar way, and sometimes it makes sense to do them vector. You could always do vector and you'll never sort of be wrong there, but sometimes it just makes sense, and you'll see as we continue on into some of the examples. But let's say we have this, whatever, maybe we're looking from the door from the top or something. So when it rotates around this axis, and then we have a force. I guess this wouldn't actually be a door, but we have a force acting down on it, so it's horizontally down. And let's see, this is point A, this is point B, where the force is happening. This here, this would be the position vector, AB, which also equals the position vector of B with respect to A. You can write it either way, but with both of those, that means it's going from A to B, or you're at B, but with respect to A. So you'll want to keep that straight. And then some other important things here is this distance. So the force is acting straight down. It's right here. So this distance along the x-axis in this drawing is the perpendicular distance. And that's important for these moments. And then what this creates is this moment about that point A. So that moment about A. So you can calculate moments two different ways. So one way is scalar. So the moment And when we do that, basically the moment's coming out of the board. So if we do our fingers around the way the arrow is pointed, and then our thumb points out, so that's pointing towards us, is positive, is what that denotes. That equals the perpendicular distance times that force. So in our drawing over here, it would be this perpendicular distance times that force. I'll write that down as times that force. The other way to do it is vector. And with that, it's the moments about whatever point A equals that position vector of B with respect to A, and it's a cross product with the force. So those are sort of the big equations that'll be important. So sometimes with the scalar, sometimes it just makes sense the way the problem's set up, where it's really easy to tell the perpendicular distance and the force, and all you need is that magnitude. If you also need the direction and it's weird stuff, then you go with the vector. And certainly when we get into 3D cases, then you want to go with the vector format. And then another point is that the sense of the moment is about an axis point passing through that point. So like here we have that point A, so the moment is through an axis, like coming in and out of point A. So note sense of the moment is about the axis passing through a point. One thing that's important as you start thinking about this is the right-hand rule, and I encourage you to look in the textbook to see some of the drawings of this, and we'll talk about it some in class. But basically with the right-hand rule, it'll help us figure out the direction of a moment. Make sure you understand this right-hand rule. So, use to figure out direction of a moment. So let's say we'll do a couple of different cases. Let's say we have this, and we're interested in the moment about point A, and let's say we have a force that's going straight up here. So force straight up. Basically with the right hand roll, so that A is the axis of rotation, we take our right hand and take our fingers along from A to that force, and then we curve the fingers in the direction of the force. So right now my hand is facing to the left, my whole hand, and then I do my fingers pointing up like that moment, and then my thumb is pointing down, so that means that the moment is negative. It's going into the board. So this is a negative moment. It's going into the screen, I guess, not board. If we did it, same thing, so we have another one, and we have point A over here, and we're interested in that moment about A, and we have our force now is pointing down and on the right side. So now I take my fingers from point A to that force, so now my fingers are pointed to the right, and then do the fingers down in the direction of the force. So now my thumb is going into the screen. So that's also a negative moment. So now we'll do another one where they're not perpendicular. So let's see. So here's our example. We have point A. We have this force, say right here. Is our force. So again, A, and then I put my hand in the direction from A to that point, to the tail of the point, or the force vector, and then curve my fingers in the direction of the force, and then my thumb's going into the board. So again, this is a negative moment. Let's do another one. So point A, let's say we have the force going up in this direction. So with this one, we do our hand from A to F, and then curl our fingers up in the direction of the force. So now my thumb is pointed towards me, so it's coming out of the screen. So this would be a positive moment. Let's see, maybe we'll just do one more. So we have point A, and then we have a force going up. So with this, we go from A to F. I guess that's pretty similar to the other one. Curl the fingers in the direction of the force, and my thumb's sticking up, so this one's a positive moment. So make sure you understand that that right hand rule. The figures in the book might actually be helpful for that. So we mentioned for the vector format that we use cross product. So the moment about A equals R of B with respect to A crossed with the force. So you need to review cross products to make sure you understand how to do those. There are a couple of different ways. I'll start by explaining the determinant method. Y'all have probably all seen this before, but make sure you review it and make sure you understand it. So let's say we have a vector A and then another vector B. And the A vector is AX. If we write it in Cartesian format, it's AXI plus AYJ plus AZK. So I'm just telling you what the vectors are. And then B vector is BXI plus BYJ plus BZK. So if we want to take the cross product of those two, so A cross B, those are both vectors, then we can use the determinant method. And basically with that, we have I, J, K along that first row. And then we have the first one we're doing is A cross B, so the A, so AX, AY, AZ, and then BX, BY, and BZ. So basically with this, we just take, we start with the I, so I'm going to need a different color. So we do I, and then times AZ, or AY times BZ, times this, minus AZ times BY. So you basically cross out everything from the I. So A cross B equals I times AY minus BZ. And then we do minus, let's see, I'm going to do this a different color, maybe blue, minus J. So now we're doing J, so we basically cross out those and that. Minus J of AX times BZ minus AZ times BX. And then for the last one, we do plus K times, so K, so we're crossing out horizontal and vertical, of AX times BY minus AY times BX. And that's the determinant method for figuring out cross products. And I just was looking over really quickly my notes, and I apparently talked but didn't write down what I was supposed to. So for the I, it's AY times BC, but AY times BZ, excuse me. So AY BZ minus AZ BY. So that's the determinant method. The other thing, sometimes you can actually figure out the direction and stuff on your own. So we use, I think one of my students named this the sort of rainbow method. But basically, so say you were just crossing two vectors and it was I cross J. I'm just going to call it rainbow method. let's say we're crossing 3i crossed with 5j. What you can do is look at this rainbow. So I, J, K. And basically if you do I cross J, then it's going to be positive K. And if you go in the opposite direction, it's negative. So I cross J is positive K. J cross K would be positive I. And so if it goes around in that direction, then it's positive. If it goes in the other direction, so J cross I, so you're along this one, then that would be negative K. Or if you did K cross J, you get negative I. So for this example, 3i cross 5j, so it's I cross j, so it's moving in that direction, so that would be positive K. So that'd be 15K. If we did 2j cross 3i, so j cross I, so we'd be moving counterclockwise, and that would give us a negative K. And then we did the 2 times 3, so negative 6K. Let's see. 4K cross 2I. So K cross I, so we're going in the clockwise direction, so that's going to give us a positive J. And that'll be 8J. And maybe we'll do one more. Let's see. 7J cross 3K, so J to K, so that's moving in the clockwise direction. That's going to equal positive I, and then it'll be 21I. So that'll be helpful for you as you're moving forward with these problems. So the last thing I want to talk about for this chapter are 3D moments. And basically the main point with these, so when we move from 3D into move from 2D into 3D, it's the same thing. The equation's the same. You just really want to use the vector method for the most part. So the moments about an axis Q equals R OP crossed with the F. So we want to use the vector method. Other than that, it's the same as 2D moments. And for this equation, that R from the origin to point P is any position vector from point 0 to any point P along the line of action force. So the moment is just you take any position point from, or any vector from point O to any point along the line of action of the force. So if the force was, say, this direction, we could take, and this is basically because it's a cross product, but say the origin was here, is the origin, we could take that position vector to be, like that, so R, O, P. So that could be our P, or we could pick a point over here, that could be our P. We could do that, or we could go back here. And the reason why that works is because we're just doing the cross product. And so with the cross product, we're just interested in that it gives us that perpendicular distance to that force line. So you can pick any of those position vectors. I lied. There's one more thing I want to talk about, and that's couples. So with couples, you have two parallel forces with the same magnitude but opposite directions, and they're separated by a perpendicular distance d. So with these, they have no resultant force because because they cancel out. Same magnitude, but opposite directions. And separated by distance d, or perpendicular distance. So for these, the sum of the forces, the resultant forces equals 0, because basically you're going to have one force in one direction, and they're parallel, separated by this distance d. But since they're parallel and the same magnitude, so if this is A and B, the sum of the forces are going to equal 0, because it'll be, say that was in the J direction, so that would be sum of the forces resultant equals A, so we're going to say the magnitude is just M times in the positive J direction minus the same magnitude for both of them, and this one's in the negative J direction, so that just equals 0. It produces an actual rotation. So think like a steering wheel. So for a steering wheel, I don't know if any of y'all have driven older cars, but with those they have these really big steering wheels, and that's partially just so we can get more torque on them. But say you have your hands, you're making a turn, and you're making a left turn, you have your right hand, you're pushing up, your left hand you're pushing down at the same magnitude. That just creates that couple. So because it doesn't have a resultant force, it's just a special case of a moment. So this is a and because the resultant force is 0, it's also called a free vector. So the couple can be moved around anywhere. It just depends on that distance between the two forces. And what we do couple is C with a line over it. That's that position of B to A, crossed with the force. Or you can do the, if you just did with the magnitudes, the scalar, it's the perpendicular distance times that force. And that, the R is from any point to any point on each of the vectors. So if we say this is point B, this is point A, this would be R of B to A, and this here would be that perpendicular distance, because that does need to be in a certain direction. So that's perpendicular right there, and yeah, that's the two forces or whatever. So so that's just a special case, and they're called couples.